Hello and welcome to today's session on advanced cryptographic concepts, part of the CompTIA SecurityX CAS-005 series. In this lesson, we will explore topic 3.7.1, Post-Quantum Cryptography, also known as PQC. This is an emerging field focused on protecting our digital systems against the capabilities of quantum computers. Let's break it down into key areas. First, we'll define what post-quantum cryptography is. Then we'll compare it to traditional algorithms like Diffie-Hellman and Elliptic curve cryptography, or ECC. We'll then explore how quantum computers threaten current cryptography. And finally, we'll look at real-world examples and emerging implementations. What is post-quantum cryptography? Post-quantum cryptography refers to cryptographic algorithms that are secure against the potential threats posed by quantum computers. These algorithms are designed to run on classical computers, but remain resistant to quantum attacks. Unlike traditional cryptography, which relies heavily on mathematical problems like prime factorization or discrete logarithms, post-quantum algorithms are based on hard problems like lattice-based cryptography, code-based cryptography, multivariate polynomial equations, and hash-based signatures. These problems are considered much harder for quantum computers to break. Why are traditional algorithms at risk? Let's talk about Diffie-Hellman and ECC, or elliptic curve cryptography. These are two widely used public key cryptographic systems. They rely on mathematical problems that are currently difficult for classical computers to solve. However, quantum computers are a different story. With Shor's algorithm, a quantum computer can solve these problems efficiently. That means it could potentially break the encryption used in most websites, email, banking systems, and more. For example, if you use ECC for your secure communications today, a large-scale quantum computer could, in the future, recover your private key from your public key within seconds. This is not just a theoretical threat. It's a matter of when, not if, quantum computers become powerful enough. What is Shor's algorithm? Shor's algorithm is a quantum algorithm developed by Peter Shor in 1994. It can factor large integers exponentially faster than the best-known classical algorithms. That's a major concern because many cryptographic systems rely on the difficulty of factoring large numbers, like RSA. This means that RSA, Diffie-Hellman, and ECC are not considered safe in a post-quantum world. What makes PQC different? PQC algorithms use different mathematical structures that are believed to be resistant to both classical and quantum attacks. Here are a few notable examples. Lattice-based cryptography uses mathematical lattices. One example is a learning with errors LWE problem. NIST finalists like Crystal's Kyber for encryption and Crystal's dilithium for digital signatures fall in this category. Hash-based signatures. These rely on security of cryptographic hash functions. A good example is XMSS, the Extended Merkle Signature Scheme. Code-based cryptography, based on error-correcting codes. One example is classic Michaelis, which has been studied for decades and is considered quantum-safe. Multivariate polynomial cryptography uses equations with multiple variables. Examples include Rainbow, though not all of them have proven secure during standardization. Real-world example. Let's take Crystal's Kyber as an example. This is a key encapsulation mechanism. It's fast, compact, and resistant to known quantum attacks. It's currently one of the top candidates in the NIST Post-Quantum Cryptography standardization process, which aims to finalize quantum-resistant algorithms for public use. Crystal's dilithium, a digital signature scheme from the same family, is also in the final round. These are likely to replace RSA and ECC in many applications, from browsers and VPNs to secure email and software updates. What should security professionals know? As a cybersecurity leader, your responsibility is to plan ahead. You need to understand that current encryption methods will not hold up in the long term. Data encrypted today could be captured and stored by adversaries, only to be decrypted once quantum computers are ready. This is known as harvest now, decrypt later, and it's a real threat. By implementing quantum-safe encryption early, you ensure long-term confidentiality. Also, stay updated with the NIST PQC standardization process and start testing implementations in your own infrastructure. Summary. Let's quickly review. Post-Quantum Cryptography is designed to resist quantum computer attacks. Algorithms like RSA, Diffie-Hellman, and ECC are vulnerable to quantum techniques like Shor's algorithm. PQC uses new mathematical problems like lattices and hash-based systems to ensure security. Examples include Crystal's Kyber, Crystal's dilithium, and classic Michaelis. Quantum-safe cryptography is the future, and that future is coming fast. Be proactive. The shift to post-quantum systems will be a major transition in cybersecurity. Start learning, testing, and preparing your organization today. Thanks for joining this session on post-quantum cryptography. In the next episode, we'll explore more about implementation strategies and key transition challenges. Stay secure, and I'll see you in the next one.